In this video, we'll start studying the notion of group actions. So let G be a group. We're going to let A be a set. Then a group action is a function from the Cartesian product of G with A to the set A. And so this is the only time I'm ever going to denote the function by sigma. And from now on, rather than writing sigma of GA, I'm just going to write G dot A. Because the point is you've got a function on ordered pairs, and every ordered pair is of the form G comma A, where G is an element of the group, and A is an element of the capital set A. And in order to be a group action, we have two requirements. The first requirement is this one, which is that if I take two elements of my group, G1 and G2, and an element in my ground set A, if I act on A by G2 and then act by G1, then I get the same result as if I multiply G1 and G2 together and then act on A. And then the second requirement is that acting by the identity element, it gives you the identity function. 1.A is A. So one way to think about this is that if you take a vector space, V, and you take every vector space is a vector space over some field, and if you haven't taken Algebra 2, you could just assume the field is, say, real numbers for now. Well, non-zero real numbers form a group under multiplication, and there's this operation in linear algebra you call scaling a vector. And these are the two of the axioms about scaling a vector that only involve the multiplication operation for scalars. And so group actions are sort of a generalization of vector spaces, only you've forgotten what addition is on both sides. So you only have multiplication to work with. And so this says if you scale A by G1 and you scale A by G2, you get the same result as if you scale A by their product. And in fact, that's the example I use. So suppose R take away 0 acts on R to the n by this action. So R times this sequence, x1 through xn, is given by coordinate-wise multiplication by R. And multiply all the elements simultaneously by R. Let's actually check that this is a group action. Well, let's take two non-zero real numbers. Let's call them R and S. Well, if I multiply through by S, it's the same as sx1 comma sx2 dot 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 sxn. This is in my new n tuple. And I'm going to scale that by R. The result is R times sx1, R times sx2, so on and so forth. So the ith coordinate here is R times s x sub I. But of course, these three are real numbers, and multiplication of real numbers is associative, so that ith coordinate is also R times s times xi, which is what you get if you multiply the n tuple by R times s. And so we see that just like in linear algebra and multivariable calculus, scaling a vector by two quantities in succession is the same as scaling by the product of the scalars. And it's not too hard to show that multiplying by 1 just gives you the tuple back. So this is a standard group action. Often there's another common group action called the left regular action, but I like to talk about a generalization of it that gives us an excuse to remind ourselves about cosets. Let H be a subgroup of G. Then it turns out that G actually acts on the coset space. Remember, this is the set of all cosets, so good reminder here. That's all things to the form G comma H. G times H, where G is an element of G. And we remind ourselves what is a coset. things that form little g times little h as little h runs through the subgroup. So this is a fact that's worth noting. In modern algebra, we study the fact that the coset space forms a group if and only if H is a normal subgroup of G, but it turns out that G mod H always comes with a group action by G, no matter what. And this is the group action. The group action is given by G times this coset is given by G prime H. Note here that I'm working with, left cosets. If you work with right cosets, this action doesn't work. You need to work on the right and have a right action instead. Of course, it turns out we have more than two properties to check. First, you actually have to check well-definedness. I'm defining this action in terms of the coset representative, and whenever you do something in terms of coset representatives, you have to check that it didn't depend on my choice. In other words, if I replace G prime with G double prime, can I guarantee that the coset G prime H is equal to G double prime H? Well, let's check that. Suppose these two cosets are the same. Then by one of the standard properties of cosets, G prime inverse G double prime must be in my subgroup H. What do I want for well-definedness? I want to guarantee that these two cosets, G prime H, is equal to G double prime H. That's equivalent to saying that the inverse of this coset representative times this coset representative is an H, which means I need to show this calculation. Well, let's just reverse engineer. What is this calculation? Well, the inverse of the product is the product of inverses in reverse order. And now you see that we have a G inverse times G together, and they cancel, and we get G prime inverse times G double prime, which is the thing we assumed was an H in the first place. So this weird product is an H because it's actually equal to the thing we started with. So our action is in fact well defined. Now we need to actually show it's an action. That's just a calculation. Do this product. So G1 times G2 times GH. Well, by definition of action, this inner term is just G2 GH. By definition of action again, G1 dot this coset is the coset associated to G1 G2 G. But multiplication is associative, so we can move the parentheses over. And then we see we have the coset we get when we act on GH by G1 times G2. Note that this isn't a completely formal proof because I'm missing my quantifiers, but at this point for a graduate course, I assume that we know how to fill in the missing details. The missing details, of course, is that you need to let G1, G2, and G be in be in G in order for this calculation to make sense. Also note I've been using 1 for the identity element, but sometimes we use E, so I'll go back and forth, but I saw that the textbook was using it this way, and I started following suit without thinking about it too carefully. One has to be comfortable with both. This comes from the fact of classical examples tends to motivate why they use this notation, so we're going to continue to use the same notation, but it's worth pointing out this 1 is the multiplicative identity of the group. And so you can check 1 times GH is 1G capital H, that's just GH. Now let's continue that same example. Let's let H be the trivial subgroup containing just the identity element. Then this coset space is essentially the same thing as G because every group element is in a coset by itself. So if you carry through what we just did, the group action is given by multiplying an element by G by A. So this is given in the textbook, and this is called the left regular action. Technically, it needs its own separate proof, but it's essentially the same as the previous example. The other common example, or at least two other famous examples, are the following. The next one involves the symmetric group. Remember, this is the collection of all bijections of a set with n elements with itself. It has a natural action on the set with n elements, namely given an element in Sn, so a permutation, and an element in n, say k. Sigma.k is sigma of k. This actually can be generalized to any set x. So S of x is the set of bijections. You could prove in a proof writing course that the set of bijections is closed under composition, and bijections are invertible, so it does in fact form a group. And composition is always associative for functions anyways, from a set to itself anyhow. And then it's the exact same calculation. Given one of these bijections, sigma acting on a point is just the image of that point under that function. And it's not that hard, and I leave it to you to check that this is in fact a group action. Given that the function operation is composition, it's not that complicated. Example 4 is a bit more interesting. G also acts on itself by conjugation. So this is a very different action than the left regular action, and this one's actually a very important action in group theory. So I'm going to denote the action this way, because you can't call it G.x, because it starts to get confused with this one. This is a superscript. So what I'm doing here is, we already know a to the x is exponentiation. I'm using the same notation, only the exponent is to the left of the base instead of to the right. And the reason why becomes clear when I do the calculation. It's because if you raise to the gth power and then to the h power, you get the same thing as raising to the h times g power. But notice order matters, and that's the reason why we do it this way. If you try writing it the other direction, you get this weird fact where the order of operations changes, which just looks unusual. So this turns out to be a handy way to denote this notation. But here let's do the definition. G x to the g is gxg inverse. So this is called conjugation. Let's check that it's a group action. If I conjugate by an element g, I get gxg inverse. If I conjugate by h, I get h quantity gxg inverse, quantity h inverse. But if I move parentheses around and regroup like that, I get hg x g inverse h inverse. But the inverse of the product is the product of the inverses in the reverse order. So this right factor can be rewritten as hg inverse. And now we get what happens when you act by h times g. So this is actually group action. It's not hard to see that if you conjugate by the identity element, you don't do anything, because the inverse of the identity element is itself, and because multiplying by the identity element doesn't do anything. So here's the major theorem of the section. Given a group G in a set A, there's a group action of G on A, in other words, G acts on A, if and only if there exists a homomorphism from the group G to the symmetric group on A. So I think the early part of the textbook just points out there is a group homomorphism, but later they point out it's actually an if and only if. So I'll go ahead and prove the if and only if now. So note, naturally, given a group element G, the image under this homomorphism should be sigma of G. And sigma of G is a bijection. And of course that would get kind of awkward to write because it means I should write sigma of G of little a for an element in A. And this gets a little awkward to write, so instead of writing sigma of G, we're going to write sigma subscript G to note the image of an element under this homomorphism. So let's do the proof. Suppose G acts on A, then we need to construct this homomorphism. We're going to do it in stages. First, we're going to define this map, fix an element of G. We're going to define sigma of G of A to just be G dot A. So given an element of A, this is its output. So we see sigma sub G is in fact a function from A to A. And we've defined this for every single element of G, and so we have in fact defined a function from G to the functions from A to A, given by sending G to sigma sub G. So right now we're not actually claiming that sigma sub G is a bijection yet. That's something we still need to show. And we will do that in stages. First, we will actually show that sigma sub G sends multiplication to composition. So in other words, that sigma sub G times H is sigma of G composed with sigma of H. If we can do that, then if later we can show that G and H are in fact bijections, this actually tells you that you have a group homomorphism. So let's do that calculation. Sigma of GH when applied to A is just G times H acting on A. By definition of group action, that's the same as G acting on H acting on A. But by definition of sigma sub G, G acting on anything is just sigma sub G applied to that element. And H acting on anything is just sigma sub H applied to that element. And then finally, the application of two functions in a row is equivalent to their composition. So we have sigma sub GH is equal to sigma of G composed with sigma of H. This is for any two group elements G and H and any element A. And so this is enough to actually tell us that sigma sub GH is actually equal to the composition, since little a was arbitrary. Moreover, because 1 dot A is equal to A for any group action, we see that sigma 1 of A is always A. In particular, sigma sub 1 is the identity function. And the identity function, we will recall, is the function that's always just sends an element to itself. Finally, taking these two observations together, if I compose sigma sub G with sigma sub G inverse, I get sigma sub G dot G inverse. G dot G inverse is 1, sigma sub 1 is the identity. And vice versa, similar calculation, sigma G inverse composed with sigma G is the identity. And so what do we see? We see sigma sub G is invertible because the inverse function is sigma sub G inverse. It goes all the way back to algebra. In college algebra, you define a function to be invertible if and only if it has a function of this form satisfying this equation with respect to composition. So sigma sub G is an invertible function for any element G. In particular, that tells you it's actually a bijection. That's one of the theorems from a proof writing course. And so even though we originally defined it to just be a function, it's actually in the symmetric group on A. And so what we've managed to show is that for every G, this function is a permutation. Any two of them satisfy this identity. And so we actually have a group homomorphism from G to the symmetric group. This gives you a bit of an idea for the level of sophistication you will sometimes find with proofs. Usually the standard way of showing something as a group homomorphism would have been to actually show that your function actually sends your group from defining your domain to the group defining your codomain, and then showing multiplicative properties. And here we did something slightly different. We showed the multiplicative property first, and then showed that the codomain was actually the symmetric group. Of course, we're not done yet. There's a reverse direction. I claim that given any group homomorphism to a symmetric group, you can actually define a group action on that set A. So suppose we have such a group homomorphism. Oh wait, this is a concluding sentence from the previous proof. But now suppose there's a homomorphism from G to S sub A. Well, define the action G dot A to just be sigma G applied to A. One can easily check that the first properties of group action is well defined. Namely, if you act by G2 on A, that's just sigma of G2 applied to A. When you act by G1, that's just sigma of G1. Applying two functions in a row is equivalent to function composition. Since you have a group homomorphism, that's just sigma of G1 dot G2. By definition of our group action, that's just G1 times G2 acting on A. Similarly, 1 dot A is just sigma sub 1 of A, and one of the properties of group homomorphisms is that the identity of the domain is sent to the identity of the codomain. And the identity function sends every element to itself. So we do get that this is a group since this was a group homomorphism, we do get this property of the action. So in fact, we do have an action of G on A.